Hey everyone, Amin here with AI Plays. Today we're covering Hue Saturation Control. Let's get started. To recap, so far we've covered how a camera converts light into a bare domain image, how to correct dead pixels, how to compensate for black levels, how to adjust for lens shading, what an anti-aliasing filter is and how to apply one, how to apply auto white balance gain control, how to convert the bare domain image into a full RGB image, how to adjust the lightness scale to make a more visible image, how to convert color spaces from RGB to YCbCr, and finally, how to apply a noise filter to the two chroma channels. Before we can work on controlling hue and saturation, we need to understand what hue and saturation are by looking at the HSI color space. Similar to the YCbCr color space, the HSI color space divides color and shape information across different channels. The HSI color space is divided into hue, saturation, and intensity. Of these three channels, the intensity channel is the exact same as the luma or wide channel and holds the grayscale, shape information of the image. The hue and saturation are how images stored in the HSI color space represent color information. The hue is simply the name of a color, like red, blue, or green. It's the basic color you see. Saturation is how vivid or intense a color is. A highly saturated color is bright and pure, like a vibrant red or a deep blue. A low saturation color is a dull or washed out, like pale pink or light gray. Think of it like painting. Hue is the color of paint you choose, and saturation is how much of that color you put on the canvas. A lot of paint makes a strong, vibrant color with high saturation, whereas a little paint mixed with white makes a pale color with low saturation. To put it another way, the higher the saturation, the closer the color is to the hue, and the lower the saturation, the more white is mixed with the color. We can visualize hue and saturation with this color wheel. The hue is the angle from red around clockwise on the color wheel, which is typically represented in radians. So a hue of 0 is red, whereas a hue of pi is blue. Saturation, on the other hand, is a measure of distance from the center. A saturation of 0 means that there is none of the color specified by the given hue and only white, whereas a maximum saturation means that there is only the color specified by the given hue and no white. Saturation is on a scale of 0 to the maximum value in your data type. So if your data type is U/8, saturation is on a scale of 0 to 255. If you're working with all values 0 to 1 as floating points, then saturation is measured from 0 to 1. When it comes to converting between the chroma channels and the hue saturation channels, we can use these formulas. Hue is equal to the inverse tangent of the CR channel over the CB channel. Saturation is equal to the square root of the CR channel squared plus the CB channel squared. If you're familiar with polar coordinates, you may recognize these equations as the formulas for r and theta for converting from rectangular to polar coordinate. In practice, that's all the HSI color space is. It's a polar coordinate representation of the YCbCr color space. In fact, you can also very easily convert back to YCbCr by applying the polar to rectangular coordinate transformations. And that's all the HSI color space is. It's a polar coordinate representation that allows for easy adjustments in color type and color intensity. The purpose of hue saturation control is to run these adjustments, slightly tweaking the color representation to account for any errors created by previous steps. First, we convert from chrominance channels to hue saturation channels. Then we add a theta offset to the hue channel. This is generally a small value, like 0.01 or 0.02 radians. Next, we multiply a slight offset to the saturation channel. This value is meant to produce a very small change, so the saturation offset is also generally something pretty small, like 1.01 or 0.99. Finally, after applying the offsets, we convert from the polar HSI color space back into the YCbCr color space. Now let's have a look at the code. The HSC function takes as input the NFC image generated from the previous step, which holds the CB and CR channels after applying the noise filter. Next, delta theta is the hue offset and S is the saturation offset. The output is the HSC image, which stores both the CB and CR channels after hue saturation control. We start by making a copy of the HSC image to store the changes in, and then we extract the row and column information to loop over. Then we can begin the main loop. For every pixel, we want to extract the CB and CR channels. We add 1 since we'll be dividing CR by CB when we calculate arctangent, and we don't want to deal with any divide by 0 errors. We changed the data type in the beginning to support this change as well. Otherwise, we would end up with errors if we tried to add 1 to a pixel with value 255 in the uint8 data type. After extracting the channels, we want to calculate the arctangent to get the hue and store it in theta. Once that's done, we can add or offset delta theta to the original theta value and finalize the changes to the hue. Next, we can repeat the adjustments with the saturation values. We calculate the current saturation with the distance formula using the previously extracted CB and CR values. Then we can apply the adjustment by multiplying S, our saturation adjustment factor, to the current saturation value. Finally, to convert back to rectangular CbCr coordinates, we can apply the conversion formulas using new theta and new dist. Finally, after the main loop, we rescale the image back to uint8 and return the finalized image. Now this code works, but did you notice how for each pixel we're running the exact same isolated expressions? Unlike in previous steps, like dead pixel concealment, where you need to be aware of surrounding pixels and run comparisons, Hue Saturation Control works on each pixel individually in an isolated environment. That makes it very easy to vectorize with NumPy arrays. To do so, we'd start the same way. Change the data type to uint16 to accommodate the +1, and make a copy to store the changes to the image. But this time, instead of using for loops and extracting pixels one at a time, we extract the entire CB and CR channels as two-dimensional arrays and add one to each completely. This is the most important part. Operations run between two arrays of the same size are generally element-wise. So if you add two arrays of the same size, your result is a third array of the same size, but each index is the sum of the same index in the two previous arrays. For example, take this array with values 1, 2, 3, and 4 and call it x. Then you take this other array with values 5, 6, 7, and 8 and call it y. Now watch what happens when we print x plus y. The value in the first row and first column is 6, which came from 5 plus 1. This rule is true regardless of if you subtract two arrays, multiply two arrays, or divide them. If you take an array squared, say x squared following our old example, every element in the array gets squared. See, x squared prints out to be 1, 4, 9, 16. Finally, if you multiply a simple number by an array, every element in the array gets multiplied by that number. Sticking with our example, x times 2 is 2, 4, 6, 8. This is again true for all four of the major operations. With that, let's return to our vectorized implementation of Hue Saturation Control. We extracted the entire CB and CR channels, and then added 1 to each value. Now we can calculate theta as a two-dimensional array of the same size as CB and CR. We first divide the CR array by the CB array, and this produces a third array of the same dimensions. Then the arctangent function is applied to each element, which does not change the dimensions of the array. With that, we have an array with the hue value at each pixel. Then we add the number value, delta theta, to the array theta, which adds to each element in the array theta the offset delta theta. And with that, we have an array of the same size as CB and CR that holds all of the adjusted hue values for each pixel. Next, we can work on saturation. We apply the distance formula to the entire array at once. Inside, we square both arrays, which effectively squares every element in the array. Then we add the two together, which creates a third array of the same size. Finally, we take the square root, which gives us an array of all saturation values. Then we multiply the number value s to the array of saturation values to get an array of adjusted saturation values, same as we did with the hue. Lastly, we need to rebuild the image by converting back to CB and CR. And we can do so with the exact same method as before, the sine and cosine functions. The sine and cosine functions get applied element-wise on the theta new array, and then the resulting array is multiplied to the new dist array. Both arrays are the same size, so the multiplication is element-wise. And with that, Hue Saturation Control is basically done. We just need to clip and reset the data type, and then return the finalized image. At the end of the day, for each pixels, the operations were basically the same, but using the loop method, we adjusted each pixel one at a time, whereas the array method acted on all of the pixels at once, which made it much faster. Since hue is measured in radians and saturation is applied by multiplication, you generally don't need very large delta theta or s values. A delta theta of 0.02 and an s value of 1.01 is usually enough. When run, this module does get rid of some of the glare that used to be present near the center of the image, but it doesn't have a very strong effect on the image, which is to be expected, since our color checker image does not have any extreme or especially bright colors that would desperately need correction. And that's it for today. Next time we'll cover the noise filter for Luma. Have a great day, everyone.